Hello everyone, I'm Anupam Gohai and I welcome you all to today's session on advanced graphics in Scilab. In this lecture, we'll explore two exciting aspects of Scilab: 3D graphics and graphical user interface design. We will start by understanding the fundamentals of 3D plotting, generating plots, and customizing them to enhance visualization. Next, we will see how to export these plots as image files for use in reports and presentations. Finally, we'll dive into the basics of GUI design in Scilab, learning how to create user-friendly interfaces that simplify complex tasks. This session is designed to give you both theoretical insights and practical examples to help you integrate these tools into your projects and research. Let's get started. 3D graphics allow us to represent data in three dimensions using the X, Y, and Z axis. Unlike 2D graphs, 3D graphics add depth, making visualizations more realistic and detailed. This is useful when dealing with complex data, where understanding relationships in multiple dimensions is important. 3D graphics are widely used in different fields. In engineering design and analysis, they help in creating and testing products in CAD software. For scientific modeling, 3D graphs help visualize natural phenomena such as weather patterns or molecular structures. In education, 3D visualizations make learning more interactive, helping students understand complex concepts easily. 3D plotting is used to visualize functions and datasets in three-dimensional space. Unlike 2D plots, which use only X and Y axis, 3D plots add a Z axis, making the data more detailed and realistic. Some common types of 3D plots include surface plots, which show smooth 3D surfaces, contour plots, which highlight different levels or elevations, and 3D scatter plots, which represent data points in 3D space. In Scilab, several commands allow us to create 3D plots. The plot 3D command is used for generating surface plots which represent smooth 3D surfaces. For more control over surface plotting, we use plot 3D1 command. If we need to create a 3D scatter plot which displays individual data points in 3D space, we use the scatter tree command. These commands make it easy to visualize complex data and mathematical functions in 3D. Here is a simple example of creating a 3D plot in Scilab. First, we use max grid to create a grid of X and Y values from -2 to 2. Then we define Z as a function of X and Y axis using sin x to the power 2 plus y to the power 2. Finally, the plot 3D XYZ command generates a 3D surface plot. This helps visualize mathematical functions in three dimensions.
Now let's create a 3D surface plot in Scilab. 3D plots helps us visualize mathematical functions in three dimensions. which is useful in engineering, physics, and data analysis. We'll plot the function z equal to sine x square plus y square using the plot 3D function. To create a 3D plot, we first need a grid of x and y values. This grid defines the points in the 3D space where we will evaluate our function. Here, mesh grid generates two matrices x and y that represent coordinates in a 2D plane. From -2 to 2 with a step of 0.1. Now we define the function z equal to sine x square plus y square. This will give us the height z values at each x and y point. Notice the use of dot to the power 2, which means element-wise squaring of x and y. Now we create the 3D plot using the plot 3D function. This command generates a smooth 3D surface where z values are plotted for each x and y coordinate. To make our graph more readable, let's add a title. Now the graph has a title, making it easier to understand. Let's execute this script and see the output. Now we can see a smooth surface representing our function in 3D, where here we have created a grid using mesh grid for 3D plotting, defined a mathematical function z equal to sine x square plus y square. Using plot 3D, we generated a 3D surface plot and we added a title for better visualization. This technique is useful in many real-world applications like terrain modeling, fluid dynamics, and scientific research.
There are different ways to visualize data in 3D. Surface plots, plot 3D command, create smooth 3D surfaces useful for visualizing functions. Wireframe plots, plot 3D1 command, show the structure of the surface without filling it, making it easier to see the grid. Contour plots. Contour command display level curves which are helpful for understanding height variations like in a topographic map. These different types of 3D plots help us analyze data in various ways. When working with 3D plots, we can enhance visualizations by adding titles, labels, colors, and adjusting the view. Xtitle command helps add a title and label the X, Y, and Z axis for better understanding. To make the plot more visually appealing, we can use color map function to customize colors. Lastly, we can change the viewing angle using the view command to look at the 3D plot for different perspectives. Here is an example of enhancing a 3D plot. After plotting a 3D graph, we can add a title using 3D surface plot. We label the axis with X label X axis, Y label Y axis, and Z label Z axis to make the graph easier to understand. This small customization makes 3D visualizations more readable and professional looking. Let's take a moment to check your understanding with a couple of quick multiple choice questions. This will help you review and solidify the concepts we have covered in this tutorial. Here's the first question. Take a few seconds to think about your answer. If you answered correctly, great job. If not, don't worry. You can revisit the explanation in the video to clarify your understanding. Now, here's the second question. Take a moment to think about your answer. Let's move to the next section. Exporting plots is useful for including visualizations in reports and presentations. Instead of taking screenshots, we can directly save high quality images from Scilab. This also helps when sharing results with others, making communication clearer and more professional. In Scilab, we can save plots using simple commands. For example, access to PNG command is used to save the plot as a PNG image, while access to JPG command is used to save it as a JPG file. Here is a demo command, access to JPG GCF command then 3D plot.jpg. This will save the current figure as JPG image named 3D plot.jpg. This method ensures we get high quality images for reports and sharing. Exporting a plot in Scilab is simple and useful. First, we generate the plot as usual. Then we use the access to JPG command to save it as a JPG file with the name we choose. Finally, we check the saved file in the directory where Scilab is running. This ensures we have a proper image for use in reports or sharing. Saving plots as JPG has advantages. It is compressed format, so the file size is smaller, making it easier to store. It is also easy to share whether through email, reports or presentations. Additionally, JPG files work on almost every device and platform, ensuring that the image can be viewed without special software.
Now, let's see how to export a graph as an image in Scilab. Saving plots as image files is useful for including them in reports, presentations, or sharing results with others. We will create a simple sine wave plot and then save it as a JPG file. First, we define our x values from -2 pi to 2 pi with small steps of 0.1. This gives us smooth curves x equal to -2 pi 0.1 to Next, we calculate the sine of x values to generate y values. Now we have both x and y values. needed for plotting. Let's plot the sine wave using the plot function. This command generates a smooth sine wave graph. Now we save this plot as an image file using the access to JPG function. Here, GCF function gets the current figure and sinewave.jpg is the file name of the saved image. After running this command, the plot will be saved in the working directory. To check if the image has been saved, navigate to the working directory where Scilab is running. You will find a file named sine_wave.jpg. You can open it and see the saved graph. Now let's execute the script. You see the graph and you can see a new JPG file has been saved. If you go to the folder, you can see graph saved using the script.
GUI stands for Graphical User Interface. It is a visual way of interacting with software instead of typing commands. A GUI includes elements like buttons, menus, sliders, and other controls that help users perform tasks easily. GUIs in Scilab make it easier to interact with programs. Instead of writing long commands, users can simply click buttons or adjust sliders. This makes Scilab applications more accessible, especially for beginners who may not be comfortable with coding. In Scilab, we can create graphical user interface using built-in functions. The UI control function allows us to add buttons, sliders, and other controls to interact with our program. The figure function opens a new graphical window where we can place our GUI elements. Creating a GUI in Scilab is easy and follows three simple steps. First, we initialize the GUI window using the figure function. Next, we add controls like buttons or sliders using UI control. Finally, we define callback functions which specify what happens when a user interacts with the GUI. Here is a simple example. This code creates a button labeled "Click Me." When clicked, it displays the message "Button clicked" in the console.
Now we'll create a simple graphical user interface GUI in Scilab. GUIs make it easier for users to interact with software using buttons, sliders, and other controls instead of typing commands. We will create a simple button with a message on the top displayed as "Click Me." First, we need to create a window where our button will be placed. We do this using the figure. Now we'll create an interactive GUI using a button in Scilab. Our example will use a button to display a sine wave graph. First, we define a function that will plot the sine wave whenever the button is clicked. The CLF command clears the figure before redrawing, ensuring a smooth update. This function will be called every time the button is clicked. Now we need a graphical window to display the graph and a button. We do this using the figure command. This command opens a new window where our graph and button will appear. Next, we add a button using the UI control function. The button will allow users to view the graph. Let's understand this command. Style push button creates a button. String show graph sets the button label as show graph. Position 10, 10, 80, 50 displays the button at this position. Callback update graph calls the update graph whenever the button is clicked. Now we run the script and a window should appear with a button at the bottom. As we click the button, the graph appears. You can see the sine wave. This is a basic example of interactive plotting using GUI elements. You can modify this script to change the different functions whenever required.
Before we wrap up, let's quickly check your understanding of the concepts we have learned. Here are two multiple choice questions for you to think about. Take a moment to reflect on your answers. If you got it right, excellent. If not, you can review the explanation in the video. Here's the next question. Great work on these questions. Now let's summarize everything we have learned in this session. We began by exploring the fundamentals of 3D graphics, a powerful tool for visualizing data in 3 dimensions. We learned how to generate various types of 3D plots using commands like plot 3D and scatter 3D, and how to customize these plots with titles, labels, color maps, and view angles to make our visualizations more insightful and professional. Next, we discussed the process of exporting plots to image files, focusing on formats like .jpg, which are essential for integrating visuals into reports and presentations. This step not only makes your work more shareable but also adds polish to your deliverables. Lastly, we introduced the concept of graphical user interface in Scilab. We learned the basics of creating GUIs, including the use of UI control to add interactive elements such as buttons and sliders. GUIs make applications more accessible and user friendly, allowing non programmers to interact with their work efficiently. In summary, today's session emphasized how Scilab's graphics capabilities, both 3D visualization and UI design, can enhance your projects whether in academia, research, or industry. To encourage you to practice what you have learned and explore advanced features to fully leverage Scilab's potentials. I encourage you to practice what we have learned and explore more advanced features to fully leverage Scilab's potential. In summary, today's session emphasized how Scilab's graphics capabilities, both 3D visualization and GUI design, can enhance your projects whether in academia, research, or industry. I encourage you to practice what you have learned and explore more advanced features to fully leverage Scilab's potential.